July 1st started like any other day at the Atlas Telescope facility in Chile. Astronomers were conducting routine monitoring of near-Earth objects when their computers flagged something that shouldn't exist. Racing through our solar system at nearly twice the speed of any previous interstellar visitor was an object that would soon shatter every prediction scientists had made about visitors from deep space. The numbers were staggering. This thing was moving at 58 kilometers per second, more than double the velocity of Mercury, our solar system's fastest planet. To put that in perspective, while Apollo astronauts took 3 days to reach the moon, this mysterious visitor could make that same journey in just over an hour. The object, quickly designated 3I Atlas, was following a hyperbolic trajectory that confirmed what astronomers feared and hoped for simultaneously. This was our third confirmed interstellar visitor, and it was unlike anything they'd seen before. But here's where the story takes a darker turn. Within weeks of the discovery, teams of scientists realized they were witnessing something that challenged fundamental assumptions about how objects from other star systems should behave. The visitor was supposed to quietly drift past Mars, a predictable cosmic traveler making its one and only passage through our neighborhood before vanishing forever into the void. Instead, 3I Atlas had other plans. What happened next would trigger emergency protocols at observatories worldwide, force NASA to issue official statements, and spark a heated debate between Harvard professors and space agency scientists about whether we were witnessing the natural phenomena or something far more disturbing. The race was on to decode the secrets of an object that seemed determined to break every rule in the book. As 3I Atlas barreled toward its closest approach to Mars, teams of astronomers found themselves asking a question that would keep them awake at night. Was this really just a comet from another star system, or were they tracking something that had been deliberately sent our way? The scientific community was already on edge when Harvard professor Avi Loeb dropped a bombshell that sent shockwaves through astronomy circles and straight into the public consciousness. Loeb, the same scientist who had previously suggested that Oumuamua might be alien technology, was now setting his sights on 3I Atlas. His claims were explosive and impossible to ignore. In a controversial paper that would later be called Nonsense by fellow scientists, Loeb questioned whether 3I Atlas was what it appeared to be. He suggested the object might be a sophisticated alien probe, possibly even hostile, designed to study our solar system or worse. The implications were terrifying. If Loeb was right, humanity wasn't just witnessing a rare astronomical event. We were being surveilled by an advanced civilization that had sent technology capable of interstellar travel. The media explosion was instant and devastating. Headlines screamed about alien spacecraft approaching Earth, with some outlets claiming scientists had agreed that 3I Atlas was preparing for a surprise attack in November 2025. Social media platforms erupted with theories ranging from peaceful first contact to invasion scenarios. The public panic reached such levels that NASA was forced to take the unprecedented step of issuing official statements. NASA's response was swift and unambiguous. Agency scientists publicly debunked the alien spacecraft theories, explaining that every observed behavior of 3I Atlas could be explained by natural cometry processes. They emphasized that the object posed no threat to Earth and would pass safely by at a distance of over 270 million kilometers. But the damage was done. The seed of doubt had been planted. What made this controversy particularly explosive was the timing. 3I Atlas was exhibiting behaviors that even NASA admitted were unusual for a comet. Its brightness was increasing in ways that defied models, its chemistry was unlike anything seen in solar system comets, and its structure seemed to violate basic understanding of how these objects should behave. While NASA maintained that natural explanations existed for everything they observed, the public couldn't shake the feeling that something extraordinary was happening. The debate split the scientific community down the middle, with traditionalists insisting on natural explanations, while others quietly wondered if Loeb might be onto something. As 3I Atlas continued its relentless approach toward Mars, the question lingered. Were they watching the universe's most unusual comet, or were they tracking evidence of intelligence from the stars? Just when astronomers thought they had 3I Atlas figured out, the object pulled off a stunt that left even the most experienced comet hunters scrambling for explanations. Over the span of just 48 hours, this supposed predictable visitor from deep space erupted in brightness, glowing 6 times brighter than any cometry model had predicted possible. The explosion wasn't subtle. Amateur astronomers in Australia were the first to sound the alarm, posting measurements to the Comet Observation Database that showed light output surging overnight. Within hours, alerts were flooding in from observatories across the globe as the object transformed from a faint smudge, barely visible through telescopes, into something that was rewriting the rules of cometry behavior in real time. But the brightness surge was only the beginning of the mystery. As telescopes locked onto the rapidly changing object, they discovered something that made veteran astronomers question decades of experience. 3I Atlas was glowing green, not the typical red or blue of distant comets, but a vivid, almost electric green that seemed to pulse with energy. The color was so intense and unusual that it triggered immediate speculation about exotic processes taking place within the object's core. The green glow presented a puzzle that traditional cometry science couldn't easily solve. Normally, green comets owe their color to diatomic carbon, but spectroscopic analysis revealed something shocking. The expected carbon emission lines were completely absent. Instead, astronomers discovered that 3I Atlas had an extraordinary carbon dioxide to water ratio of 7.6, far higher than any known solar system comet. This alien chemistry was driving processes that had never been observed at such distances from the Sun. Teams of spectroscopists worked around the clock, sharing raw data and calibration scripts as they tried to decode what was happening inside the expanding coma. The structure they were observing was almost incomprehensible in scale. A glowing envelope nearly half the diameter of the Sun, stretching across hundreds of thousands of kilometers. This wasn't just a visual effect or a photographic trick. The coma was a real, physical phenomenon that was scattering sunlight on a scale rarely seen in the outer solar system. As the brightness continued to fluctuate unpredictably, major observatories activated emergency protocols. The Hubble Space Telescope carved out urgent imaging slots. The James Webb Space Telescope secured committee-approved windows for infrared spectroscopy, and ground-based facilities scrambled to track an object that was evolving faster than their instruments could follow. Every measurement revealed new anomalies that pushed the boundaries of known cometry physics to their breaking point. The clock was ticking, and astronomers around the world knew they were running out of time to solve the mystery of 3I Atlas. As the object barreled toward its October 3rd flyby of Mars, a cruel twist of orbital mechanics was about to rob Earth-based telescopes of there to observe what might be the most important astronomical event of the decade. The problem was geometry. As 3I Atlas approached the inner solar system, the angle between the comet and the Sun, known as solar elongation, was shrinking day by day. Observatory directors watched helplessly as their viewing window narrowed, knowing that once the angle dropped below 30 degrees, even the most powerful telescopes on Earth would be blinded by solar glare. The most dramatic phase of the comet's evolution would unfold beyond the reach of human eyes, hidden in the Sun's overwhelming brightness. This created a desperate scramble for observation time that resembled a planetary defense exercise more than routine comet research. Observatory schedulers across multiple continents found themselves coordinating emergency sessions, with science teams competing for every available minute of telescope time. The Hubble Space Telescope, already oversubscribed with high-priority projects, had to recalibrate on the fly to keep pace with the comet's rapid changes while avoiding dangerous instrument saturation. The James Webb Space Telescope faced its own challenges as mission planners worked to secure rare committee-approved windows for mid-infrared spectroscopy. When JWST's instruments finally locked onto the coma on August 6th, they captured data that would fuel months of analysis, if there was time to process it all before the blackout period began. Every spectrum revealed new chemical signatures that had never been seen in solar system objects, adding urgency to an already time-critical situation. Ground-based observatories weren't faring much better. The Gemini South Observatory in Chile grabbed sequences of optical and infrared snapshots whenever weather permitted, while teams monitored subtle changes in coma structure and color that evolved from night to night. Even NASA's Spherex All-Sky Surveyor, never designed for rapid follow-up observations, was pressed into service to provide broad wavelength coverage of the comet's evolving spectrum. The coordination required a level of international cooperation that astronomy hadn't seen since the detection of gravitational waves. Observatory directors juggled competing requests while data pipelines ran overnight processing sessions to distribute raw images before the next night's observations. Slack channels filled with debates over filter choices and exposure times as every observation became precious, knowing that each night brought them closer to the inevitable blackout. By early October, the writing was on the wall. Earth's most sophisticated telescopes would soon be helpless as 3i Atlas slipped into the sun's glare, carrying its secrets with it. The final hope for unraveling the mystery would depend on a handful of spacecraft already circling Mars, machines never designed for this kind of emergency, but now representing humanity's last chance to decode an alien visitor before it vanished forever. The green glow radiating from 3i Atlas wasn't just unusual, it was completely rewriting what scientists thought they knew about interstellar chemistry. As spectroscopists around the world pored over data from the most advanced telescopes on and off Earth, they uncovered evidence that this visitor from another star system was operating under rules that defied everything in their textbooks. Traditional green comets get their color from diatomic carbon, a well-understood process where carbon molecules fluoresce in distinctive wavelengths when struck by sunlight. But when teams searched the spectra of 3i Atlas for these telltale swan bands, around 510 nanometers, they found nothing. The expected carbon signature was completely absent, even as the green glow intensified to levels that lit up imaging sensors across multiple observatories. What they found instead was even more shocking. The James Webb Space Telescope's August readings revealed a carbon dioxide to water ratio of 7.6, a number so extreme that it placed 3i Atlas far outside the range of any known solar system comet. Where water typically dominates the chemistry of comets from our neighborhood, this interstellar visitor was powered by ancient carbon dioxide ice that had somehow survived millions of years traveling between the stars. The implications were staggering. This wasn't just a different type of comet, it was evidence of chemistry forged in another star's planetary nursery, carrying the signature of processes that occurred in a completely different stellar environment. The green glow, scientists determined, was likely coming from atomic oxygen emission at 5,577 angstroms, produced when solar ultraviolet radiation and high-energy electrons shattered the abundant CO2 molecules, creating a factory for green photon emission on a scale never before observed. Dr. Lena Sado, lead spectroscopist with the JWST team, described the challenge as chasing a moving target with a shifting personality. Each new spectrum captured a system in constant flux, where alien chemistry and extreme physics collided in ways that pushed the boundaries of known science. The comet wasn't just visiting our solar system, it was teaching humanity about the diversity of materials and processes that existed in the wider galaxy. But the mystery deepened with every observation. Laboratory experiments and previous comet studies supported the atomic oxygen theory, but 3i Atlas was producing this effect at distances where it shouldn't be possible. Even at 2 astronomical units from the Sun, conditions were somehow right for this exotic mechanism to dominate, outshining dust scattering and creating the eerie signature that had captured the world's attention. Alternative explanations were tested and rejected one by one. Teams searched for carbon monoxide fluorescence, exotic dust scattering effects, and rare plasma phenomena, but the evidence kept pointing back to the same conclusion. They were observing chemistry that had never been seen before in our solar system. The absence of expected carbon signatures wasn't a measurement error. It was proof that 3i Atlas was following rules written by a different star. As if the green glow wasn't puzzling enough, 3i Atlas revealed another feature that sent physicists scrambling for explanations and fueled even more speculation about its true nature. Stretching away from the comet's nucleus wasn't the typical tail that should point away from the sun, but something that violated basic cometry physics, an anti-tail that pointed directly toward our star. The structure was visible in both Hubble images and ground-based telescopes, a sunward streak that persisted for weeks and defied the standard explanation astronomers use for such phenomena. Normally, anti-tails are temporary illusions created when Earth crosses a comet's orbital plane. causing perspective effects that make debris appear to point the wrong direction. But the geometry was all wrong for 3I Atlas, and the feature's persistence suggested something far more substantial was happening. Plasma physicists and orbital dynamicists focused on the mechanics behind this impossible structure. Unlike typical comets dominated by water ice, 3I Atlas was powered by carbon dioxide sublimation, and its outgassing was anything but uniform. Solar radiation was hitting the nucleus at steep angles, driving powerful jets of gas and dust primarily from the sun-facing side. This uneven activity was launching material outward, but not in all directions equally. The strongest jets occurred where sunlight was most intense, creating conditions that pushed the traditional snow line much farther toward the sun than in normal comets. Dust grains launched along this axis were larger and more resilient, able to survive both radiation pressure and intense heat for much longer periods than the fine particles that create typical comet tails. The result was a real physical anti-tail composed of massive grains that could persist across tens of thousands of kilometers before finally succumbing to solar radiation. Computer models indicated these grains were at least 10 microns across, large enough to resist the solar wind and maintain their sunward trajectory. Their survival depended on both size and composition, with darker, less volatile materials mixed into the carbon dioxide ice, allowing some particles to endure the journey that would destroy smaller debris almost instantly. But the anti-tail's behavior added another layer of mystery. Its brightness dropped off exponentially along its length, exactly matching predictions for grains being steadily destroyed by sunlight rather than simply scattered into space. This wasn't just a visual artifact. It was evidence of an active process where interstellar material was being systematically dismantled by our sun's energy. Some researchers speculated about more exotic explanations. Could electromagnetic forces be creating narrow streams of charged particles? Might plasma interactions be distorting the expected flow of debris? A few even wondered aloud whether they were observing artificial structures or self-organizing systems beyond current scientific understanding. But every measurement kept pointing back to the same conclusion. This was natural physics, pushed to extraordinary extremes. Dr. Rafael Ortiz, a plasma physicist working with the Mars Orbiter campaign, put it simply: if you want proof of the extraordinary, you need to rule out the ordinary first. So far, the anti-tail is a triumph of natural mechanics, operating under conditions we've never seen before. The question remained whether those conditions were truly natural or the result of engineering beyond human comprehension. As Earth's telescopes succumbed to solar glare, an unlikely savior emerged in the form of robotic explorers already circling the red planet. Mars, positioned perfectly to observe 3I Atlas during its critical approach phase, suddenly became humanity's most important observatory, equipped with instruments never designed for this unprecedented emergency. The transformation was remarkable. Spacecraft that had spent years studying Martian geology and atmosphere were rapidly reprogrammed for an entirely different mission. Mission controllers across multiple space agencies found themselves coordinating the most complex interplanetary observation campaign in history, turning Mars orbiters into an improvised alien hunting network with capabilities that surpassed anything available on Earth. NASA's Mars Reconnaissance Orbiter brought the high-rise camera, capable of resolving objects as small as a desk from orbit. With its 0.3 meter per pixel resolution, HiRISE could theoretically spot the nucleus of 3I Atlas if the tracking geometry cooperated. But following a comet racing at 58 kilometers per second, millions of kilometers away, pushed both hardware and software beyond their design limits. Teams at the University of Arizona and JPL ran constant simulations, tweaking exposure times and fighting for precious imaging windows while battling the risk of equipment damage if the sun crept into view. The European Space Agency's Mars Express contributed the high-resolution stereo camera, perfectly suited for capturing the full sweep of the comet's massive coma and anti-tail. Its color filters could separate dust from gas, while stereo imaging might reveal three-dimensional structure in the expanding cloud. German operations teams coordinated with ground-based astronomers to time exposures for optimal viewing angles as the comet crossed Mars's orbital plane. The ExoMars Trace Gas Orbiter added another dimension with its CAS-SIS imaging system and NOMAD spectrometer suite. Originally designed to detect faint atmospheric gases on Mars, NOMAD was retasked to confirm the elevated carbon dioxide levels first detected by JWST and search for chemical signatures that had never been seen in solar system comets. If 3I Atlas truly carried chemistry from another star system, NOMAD would be the instrument to prove it. NASA's MAVEN mission joined the effort with its imaging ultraviolet spectrograph, tuned to detect emissions from atomic oxygen and carbon that might explain the mysterious green glow. Meanwhile, its plasma instruments prepared to measure how the solar wind interacted with the comet's unprecedented outflow, potentially revealing whether exotic processes were at work, or whether natural physics could explain the anomalies. The coordination required was staggering. Mission operations, centers in the United States and Europe, ran emergency planning sessions, weighing the risks of diverting instruments from routine Mars science. Every observation slot became a negotiation between engineers, principal investigators, and project managers, with safety protocols demanding that cameras avoid direct sunlight and spectrometers maintain careful calibration to prevent permanent damage. Sometimes, software patches were uploaded at the last minute to enable new tracking modes or override safety limits that had never anticipated this scenario. No single orbiter could capture the complete story of 3I Atlas, but together they formed a synthetic observatory more capable than any single instrument on Earth. As the comet approached its closest point to Mars, this improvised network represented humanity's final chance to solve the mystery before the visitor vanished into deep space forever. The final act of 3II Atlas was unfolding exactly as orbital mechanics predicted, yet somehow felt like the climax of a cosmic thriller where the main character was about to disappear forever, taking all its secrets with it. As the interstellar visitor rounded the sun for its closest approach, astronomers faced the crushing realization that the most dramatic phase of its evolution would occur beyond the reach of human observation. Perihelion arrived on October 29th, when 3I Atlas passed within 1.36 astronomical units of the Sun, closer than Mars, but still far enough to avoid destruction. At that moment, its speed peaked near 68 kilometers per second, and models predicted its activity would reach maximum intensity. The carbon dioxide ice driving its unusual behavior would sublimate at unprecedented rates, potentially creating new outbursts, color changes, or structural evolution that could finally explain its alien chemistry. But from Earth, the comet had vanished completely into solar glare weeks earlier. The most sophisticated telescopes on the planet were helpless, blinded by the overwhelming brightness of the sun. Even the Hubble Space Telescope and James Webb, with their advanced coronagraphs and precise pointing systems, couldn't penetrate the solar corona to glimpse the comet during its most active phase. Humanity's best instruments could only wait and hope that Mars orbiters would capture enough data to fill the gap. The blackout period, spanning from early October through early November, created a frustrating information vacuum. Social media buzzed with speculation about what might be happening in the hidden depths of the inner solar system. Was 3I Atlas undergoing the slow fade predicted for carbon dioxide-dominated comets? Was it experiencing final outbursts as fresh ice pockets were exposed? Or was something more dramatic occurring? Fragmentation, structural collapse, or changes that would rewrite cometry science? Computer models split into competing scenarios, each with different implications for what observers would see when the comet finally emerged from solar glare. Some predicted a gradual decline in brightness as volatile materials were exhausted, leaving only a faint remnant drifting outward. Others warned of potential fragmentation if the nucleus proved as porous and unstable as its wild activity suggested. A few models even suggested the possibility of continued brightening if deep reserves of carbon dioxide ice were suddenly exposed. The uncertainty was maddening for scientists who had invested months tracking this unprecedented visitor. Dr. Mara Valente, the comet dynamicist leading one of the monitoring campaigns, described the situation as watching a mystery novel where someone ripped out the final chapter. Every theory about interstellar objects, alien chemistry, and exotic physics would have to wait for the comet's reappearance to be tested against reality. When 3I Atlas finally emerged from solar glare in early November, it would be forever changed by its encounter with our sun. The chemistry forged in another star's planetary nursery would bear the scars of solar radiation and heating. The alien ice that had survived millions of years in interstellar space would be partially transformed into something new, Whether it retained its green glow, its anti-tail structure, or its record-breaking brightness remained to be seen. The stakes extended far beyond a single comet. 3I Atlas represented a probe from another star system, carrying information about chemistry, physics, and planetary formation processes that occurred around a distant sun. Its behavior during perihelion would test the limits of cometry science and determine whether natural explanations could account for all its anomalous properties, or whether something more extraordinary was at work. As Earth's observatories prepared for the comet's return to visibility, one thing was certain. 3I Atlas had already rewritten the textbook on interstellar visitors. Whether it would continue to surprise astronomers or finally reveal itself as an exotic but natural wanderer from the depths of space remained the greatest astronomical mystery of the decade. The Vanishing Act was complete, but the final chapter of this cosmic detective story was yet to be written.